Hello everybody, this is Dr. Christopher White. Welcome back for part 2 of Paleozoic Earth history, focusing on the late Paleozoic. So we've just completed our general overview for the Devonian, the Carboniferous and the Permian. So now we need to think about some of the cratonic sequences and the tectonic events which are going to be taking place on Laurentia during the late Paleozoic. So in terms of sequences, we're going to have two large marine transgressions, and that's going to lead to the formation of the kaskaskia and absaroka epiric seas. So we're going to have two very large marine transgressions, and you can see based on the diagram that these transgressions cover a substantial portion of North America. We also have a convergent event occurring on the west coast, that's the Antler orogeny. And on the east coast, we actually have three events taking place. We have the Acadian orogeny, the Achetan orogeny, and the Alleghanian orogeny. So, as you can see, there's lots of stuff going on in the Paleozoic, especially over on the east coast. I should point out, by the way, if we look at the diagram over here, you'll notice here we have the Devonian, here we have the Permian, Mississippian and Pennsylvanian. So this entire area marked out here in blue represents the Carboniferous. Okay, so let's start with the kaskaskia. So the kaskaskia sequence was deposited between the Middle Devonian and the Middle Carboniferous, and it unconformably overlays the Tippecanoe sequence. So, as with the Tippecanoe sequence, the basal beds of the kaskaskia sequence consist of well-sorted, mature, quartz-rich sandstones, and the sediment for these sandstones has been formed by the erosion of uplifted detrital sedimentary rocks associated with the soak, the Tippecanoe, and also just general erosion of the Precambrian basement rocks. We also have sediments being contributed by the erosion of the Appalachian Mobile Belt, so that's the Taconic orogeny, and we just have sediments generally coming from the erosion of the crystalline Canadian Shield, so all the granites and gneisses of the Canadian Shield. So this means there's a large resource of rocks which are going to provide large quantities of sediment, and a lot of that sediment is going to be quite quartz and feldspar rich. And we've already discussed that some of the sedimentary rocks which are being eroded will be related to the earlier soak and Tippecanoe sequences. Those were already quite well sorted sandstones, so when you rework them again, you take essentially a very quartz rich sandstone and you upgrade it even further to make it even more quartz rich. So where we have these sandstones, they essentially represent just a reworking of earlier material, a lot of it from the soak and the Tippecanoe sequences. So the lack of sandstones in some areas suggests that some regions were not eroded as much as others. So in areas which underwent quite high rates of erosion, obviously that you managed to erode through the sedimentary rocks of the Tippecanoe sequence and maybe the soak sequence, and you end up down at the crystalline basement, and that helps to allow you to access all of this very quartz rich rock, which you can then erode to produce very quartz rich sediments. In some areas, though, we don't see the formation of the sandstones, and that would suggest that we weren't exposing rocks which we could weather to make sandstones. That would suggest that the layer of carbonates which were deposited as part of the Tippecanoe sequence was still intact. And so this would mean that some areas were maybe not as uplifted as other areas or had lower rates of erosion. And so this means that, you didn't get the sandstone forming because you didn't have rocks exposed which you could weather to make the sandstone. So this means that in some areas, the carbonates of the kaskaskia transgression, so the kaskaskia epiric sea, sit directly on top of the carbonates from the Tippecanoe sequence. The kaskaskia transgression is going to lead to the formation of warm, shallow seas. And as we've discussed with the two previous sequences, where we have these warm, shallow seas and the water quality is quite clear, that's going to encourage the formation of carbonates. And so the kaskaskia epiric sea is just a massive carbonate producing machine. So if we look over here, we can see from this generalized diagram from the textbook that during this time period, a large quantity of North America was underwater. That obviously means less clastic sediment is being produced. That's obviously going to lead to better water quality, so clearer water. At the same time, we can also see that Laurentia is situated approximately on the equator. This obviously is going to lead to a nice warm climatic conditions. That's going to lead to nice warm water, which is also going to encourage the formation of carbonates. So in areas of the Kaskaskia Sea where we didn't form the basal sandstone, which we discussed in the previous slide, what you end up with is you end up with carbonates from the Tippecanoe sequence sitting directly below carbonates from the Kaskaskia sequence. And the problem is that these carbonates are nearly indistinguishable from one another. So the only way to actually separate these layers apart is by using the fossils to help you date, at what time each layer formed. So the majority of the Kaskaskia sequence is carbonates with associated evaporite. So this would suggest that some portions of the Kaskaskia Sea would occasionally get isolated, and that would allow for evaporation and evaporite deposition. Now there is a period of time between the Upper Devonian and the Lower Carboniferous and the Late Carboniferous, during which we actually have the formation of black shales within the Kaskaskia Epiric Sea. So these are areas of the Kaskaskia Epiric Sea that became inundated with very fine muddy sediment, but that sediment was being deposited into an area which was very, very rich in life. So there was lots of organic material. And so what you ended up forming was a muddy clastic sedimentary rock containing large quantities of carbon, which gives it a black colour. So don't worry, we're going to cover black shales in more detail in a few slides' time. So here's our situation in the Middle Devonian. We can see that we have a marine transgression taking place. We have the sea encroaching from the west and from the south. We can see that in terms of the sea, it can't really come in from the north or the east, because obviously we have the Inuitian mobile belt here, Caledonian mobile belt here, or what's left of it, should I say, and here we have the Taconic mobile belt right here. And this obviously is going to stop the sea transgressing over this high ground. So the Kaskaskia Epiric Sea can only really start coming in from the west and the south, where the terrain is flatter. As you can see by the Late Devonian, nearly all of the United States is underwater, and a substantial part of Canada is also underwater. You can see that these areas here, the high ground, so once again the Inuitian, the Caledonian and the Taconic highlands are steadily being eroded away. That's obviously going to lead to clastic sediment being deposited along the margins, but the majority of the Epiric Sea is going to be pretty clastic sediment free, and so we're going to get huge quantities of carbonate being deposited. By the early Mississippian, while the situation is pretty much the same as the Late Devonian, so nothing much happening there. And by the time we're into the late Mississippian, we can see that the Kaskaskia Epiric Sea is now in retreat. So it's heading back to the west and the south. We can also see at this point that Gondwana is about to make complete contact with Laurasia. So if we're thinking about the formation of evaporites, we need to have a look in particular at the development in Western Canada. So what we have is a situation where we go and form a very large carbonate barrier in this area, and essentially it helps to isolate a portion of the Kaskaskia Epiric Sea. So we have the Canadian Shield over here, so that's essentially dry land. We have shallow basinal limestones over here. That represents the normal Kaskaskia Epiric Sea conditions. We have our reef, which is our carbonate barrier, and then behind it we have our carbonate lagoon. And this carbonate lagoon has become isolated from the rest of the Kaskaskia Epiric Sea. So if we just go back a few slides, you can see, here we go, right there. There it is. So the restriction of this area led to the deposition of around 300 meters of evaporites. Now, what just so happened that the maturation of the underlying mudstones beneath these evaporites ended up producing oil. The evaporites themselves act as a seal to stop the oil escaping. And so underneath these evaporite deposits, we actually have some quite nice petroleum reserves. It also is very, very important to note that the evaporites which were forming due to the evaporation of the seawater are actually quite calcium chloride rich. So calcium chloride is a mineral called sylvite. And these particular evaporites are very sylvite rich. And so that means you can dig them out of the ground and you can use them to create potash, which is a type of fertilizer. So the evaporites here of the Williston Basin are not only important with regard to formation of oil reserves, but they're also useful because they help to give us a source of potash for farming. And on top of that, from a purely geologic point of view, they also show us that some areas of the Kaskaskia Empiric Sea were becoming isolated and were being allowed to evaporate away. The kind of model which is going to form these evaporites will be very similar to the model which we discussed for the Michigan Basin. So it could either just simply be the reef forms a reasonably solid barrier that stops fresh water coming in, and so the water inside the lagoon just evaporates away, or it could be that we have the reef forming a barrier which is isolating this body of water. That leads to the water at the top of the lagoon becoming very saline, very dense. It sinks to the bottom of the lagoon where it forms a layer of very, very saline rich water which sits on the bottom of the lagoon, and it's from that layer of very, very saline water that these evaporite minerals begin to form. So what about these Devonian black shales? Well, as we've already gone and discussed, most of the time the Kaskaskia Sea was just a carbonate producing machine. So that means large amounts of clear, warm, shallow water. However, for a period of time, we do have the formation of these black shales. So we see them during the Middle Devonian, and in some areas there is a change from sedimentation from carbonates to detrital sediments. So we get this shift. Now, this change resulted from the formation of new source areas associated with mountain building due to the Acadian orogeny. So along what is now the modern-day east coast of North America, we end up having the Acadian orogeny that produces high ground. High ground gets eroded, and that's going to produce large quantities of clastic sediments, which are obviously going to be deposited into the Kaskaskia Empiric Sea. So at the end of the Devonian, the black shale units, which are typically less than 10 meters thick, begin to appear. So they're best developed proximal to the margins of the Appalachian Mobile Belt, and this makes sense. So if you assume that the sediment to make them is coming from the erosion of the Acadian orogeny, which is part of the Appalachian Mobile Belt, well, obviously you're going to have most of the sediment being deposited right next to the Appalachian Mobile Belt, aren't you? The further you get away from that source of sediment, typically the thinner the layer of sediment will become. So if we look at this diagram here, we can see we have an extensive area of black shales right here. Most of that clastic sediment is going to be sourced from the erosion of the Acadian orogeny, which is going to be located about here. So that makes relatively good sense. So these late Devonian to early Carboniferous black shales are non-calcareous. They are thinly bedded, and on the whole they are fossil poor. So where present, the fossils we have are microscopic, and they consist of organisms like conodonts, which are a tiny eel-like creature, algae, and plant spores. Now this indicates that the lower beds are late Devonian and the upper beds are early Carboniferous, so we can use these fossils to date these black shales. Now, the origin of the black shales is uncertain, but we know that their formation requires a few things. Number one, we need a reduced supply of coarse detrital sediment. So what we need is lots of fine detrital sediment coming into our area. We need lots of clays and lots of silts. We don't want sands, we don't want gravels, cobbles or boulders, they're too big. So that means these areas here will have been inundated by large quantities of fine clastic sediment. We also need quite a high level of organic productivity, and most of that is going to be in the form of photosynthesizing algae. So what we're going to have is you're going to have this very fine muddy sediment being deposited into a Epiric Sea, which contains lots of nice warm water. It's near the equator, so lots of sunshine. So that seawater is going to be absolutely stuffed with billions of photosynthesizing algae. And of course, when they die, their carcasses are going to float down to the bottom, and they're going to become incorporated into the muddy sediment. Now, the reason we say it has to have a very high organic productivity is because these black shales are very organic rich. And so this obviously means that you have to be putting in a large amount of organic material. And so what we need is environments where we have lots and lots and lots of photosynthesizing algae. And it just so happens that the Kaskaskia Epiric Sea is literally the perfect setting for large quantities of algae. The final thing we need are undisturbed bottom waters. So what happens is we have a situation where we have these areas which are becoming inundated with this very fine clastic sediment. There's lots and lots of algae dying, which are their organic materials being incorporated into the sediment. But the final thing we need is we need the water at the bottom of these basins to become anoxic, oxygen free. That's going to stop the organic material from decomposing. Because remember, if there was oxygen in the water, the organic material would decompose, and so it wouldn't be incorporated into the sediment. So what we need is an anoxic bottom water. And so what happens is all of the all the algae, as they die, they float down to the bottom, and that means the water at the bottom begins to become anoxic because all the oxygen in the water gets used up through decomposition. So we have loads of organic material coming in. The decomposers begin to decompose the material, but unfortunately there's just so much of it that they end up using up all the oxygen as part of their decomposition process. And so this means that they exhaust the oxygen in that water, and so it means you end up with this layer of very oxygen poor water at the bottom of the Epiric Sea in these areas. And so this then means that any new organic material that falls into that water will not decompose. The organic material can then become incorporated into the sediment. So if we look at the distribution of the black shales, what can we see? Well, we can see that these areas here are associated with areas west of the Acadian Highlands. So we know that a lot of the clastic sediment for these areas are going to be coming from the Acadian Highlands. Now over here, along the Canadian-US border, this one's a little bit more difficult to explain. Chances are the clastic sediment is just being eroded from the Canadian Shield and is being deposited into this area. And in terms of the black shale deposits down here, in all probability there were probably several large islands in this area that were being eroded, and those are the probable sources for the clastic sediment for these black shales over here. So if we look at this map, this is for the late Devonian, we can see here we have the Acadian Highlands over here. That's obviously going to be the primary source of sediment for this area. Obviously, in terms of the black shales in this area, chances are the sediment is coming from the erosion of the Canadian Shield up here. And the clastic sediment for the black shales down here are probably coming from several large islands located in this area. So the high productivity, as I mentioned, means you get substantial quantities of organic material, which is raining onto the seafloor. So this organic material decomposes, decomposition uses up the oxygen in the water, and so that means we end up with anoxic bottom water. So the bottom layer of water becomes very, very oxygen poor. Now, the other thing we need is we can't have that anoxic water mixing with the oxygen-rich water above it. So they have to essentially stratify. They have to operate separately of one another. Now, this means that because they're operating separately, any new organic material that falls down into the anoxic water will not decompose, so it becomes incorporated into the muddy sediment. So in order to form these black shales, we obviously need lots of clay and silt and lots of undecomposed organic material. Now, the reason that we like these black shales so much is that they are an excellent source of hydrocarbons, so oil and gas. So, they're the perfect type, they're the perfect rocks for, essentially finding or producing oil or fracking to, yield oil and gas. But they're also helpful to us because they are so reducing, because they're so oxygen poor. They also become very good hosts for things like uranium mineralization. So they have multiple uses. So what's going on in the late Kaskaskia? So, quick aside, so it's worth mentioning that in the late Devonian, global temperatures begin to decrease, leading to alpine-type glaciation, so those are mountain glaciers, forming in the Acadian highlands. And so these glaciers, when they reach the sea, they'll melt. Bits of ice will break off in the form of icebergs, and as those icebergs float out into open water, of course the ice melts and it drops larger particles or larger clasts as they go along. So if you remember, these things are referred to as drop stones. So during the late Kaskaskia, we begin to see drop stones appearing within the sediments of the Epiric Sea, and so this is telling us that we have glacier formation in the Acadian highlands. So after the late Devonian to early Carboniferous black shales, carbonate sedimentation returns. So once this event is over, everything goes back to normal. So the limestones that we're forming are what are referred to as crinoidal limestones. So that means they're very, very rich in crinoid fossils. So if you look at the picture behind, you actually have a crinoid here. So a crinoid is a bit like a flower. It has a stem which attaches to the seafloor. It has a bulb at the bottom. That's actually where the animal itself lives. So that's where things like the mouth, the stomach, the digestive system, the reproductive organs are located. Then you have these arms that come off the bulb, and each of these arms have feather-like appendages. And the feather-like appendages catch little particles of food from the seawater. It passes them down the arm, and then eventually the mouth is down here at the bottom, and the food is consumed. So these crinoidal limestones are very, very common in the Kaskaskia Epiric Sea, and these crinoids are very, very useful in terms of dating and correlating these layers of rock. We also have, along with these crinoid fossils, large amounts of ooids. Ooids, if you remember, are these carbonate jawbreaker-like particles that can only really form in shallow water. We also have other shallow water indicators like ripple marks, crossbedding, and well-sorted shell fragments. All of these are going to be related to waves and wave actions. That's also telling us the water depth cannot be very deep at all. So during the mid-Carboniferous, the Kaskaskia Sea began to retreat and carbonate deposition in shallow seas stopped because the seawater is leaving. So the carbonates were followed by substantial quantities of detrital marine sediments. That's not really a surprise. As the sea begins to retreat, more of the continent becomes exposed. It can be eroded. That means you're going to produce large quantities of clastic sediments, which will obviously enter what's left of the Kaskaskia Epiric Sea. So you're going to see this shift from carbonate-rich sediments to clastic sediments instead. So exposure of Laurentia after the Kaskaskia Epiric Sea obviously results in a continent-wide erosion. So the sea retreats all the way back to the coast. That completely leaves all of Laurentia open, and so it undergoes large-scale erosion, resulting in a big unconformity. So this is our basic situation. So the Kaskaskia Epiric Sea is going to start retreating, and of course as it retreats, more of the ground here is going to become open to erosion. That's going to mean more sediment starts getting deposited into the basin. So as the Epiric Sea begins its retreat, more of this opens up. That means what's left of the Epiric Sea will become more clastic sediment rich, and so we'll steadily see the carbonates being replaced by muds and sandy sediments. Okay, so after the Kaskaskia came the absaroka sequence. So the absaroka sequence was deposited between the late Carboniferous and the early Jurassic, but we're only really going to worry about the Paleozoic bits. So the unconformity between the Kaskaskia and the absaroka sequence marks the change from the Mississippian to the Pennsylvanian. Now, the absaroka sequence is noticeably different from the Kaskaskia sequence due to the difference in tectonic regime and the sediments that are created. So we're going to see different types of rocks. So the lowest beds of the absaroka sequence occur along the west and southwestern margins of Laurentia. So we see the absaroka sequence located in the west and the south and west of Laurentia. Now this means that the east and the north and the northeast of Laurentia were probably above sea level, and therefore they could be actively eroded, producing large quantities of clastic sediments. We also see that the deposits of clastic sediments which are entering the Absaroka-Epiric Sea are thickest in the east and southeast, proximal to the Appalachian and Achetan mobile belts. So here we have the Achetan Mountains, here we have the Appalachian Mountains, and so these are obviously going to be eroding, producing large quantities of clastic sediment. So we're going to have huge amounts of clastic sediment being deposited along the coastline here. As you move away from the coastline, the amount of clastic sediment is going to get lower, and so you're going to see these sedimentary layers becoming thinner. Not really a huge surprise. So the sequence changes from non-marine detrital rocks, essentially continental rocks, into coal measures, which are marked out here in green. Then you go into a sequence of transitional rocks, which essentially represents the transition from these lagoonal environments into the marine environment. And then finally, as you move even further west, the water quality slowly clears up, and eventually right out here on the western edge of the Absaroka-Epiric Sea, you do get some carbonates forming. But most of the water here is going to be dominated by clastic sediment. So there's going to be quite a large amount of fine clastic material in the water. Lots of suspended clays, lots of suspended silt, and this is going to mean the water will not be particularly clear, and that's going to inhibit the formation of carbonates. So here's our situation in the late Carboniferous. So here is the Absaroka-Epiric Sea. We can see that a large amount of Canada is exposed. We can also see we have the Appalachian Highlands here and the Achetan Highlands right here. They're going to be actively eroding, dumping huge quantities of clastic sediment into the Absaroka-Epiric Sea. It's only in these areas where you're further away from any source of clastic sediment that you're actually going to have any hope of depositing carbonates. So most of the Absaroka sequence is dominated by mudstones and sandstones, which is obviously very different to the carbonate dominated systems of the Suck, the Tippecanoe and the Kaskaskia. So by the early Permian, you can see that the Absaroka-Epiric Sea is already in retreat, and you can see that it's becoming an isolated body of water right here. So it's trying to retreat off to the west that way, it's trying to retreat off to the west this way. Of course, it can't retreat to the east because, of course, there's what's left of the Appalachians and the Achetan Mountains stopping that happening. So now we're talking about the geology of the Carboniferous, we need to think about cyclothems. So cyclothems are repetitive patterns of marine and non-marine sediments which are common in upper Carboniferous strata. So they are the result of the interplay between non-marine deltaic, so essentially coastal processes, and shallow marine interdeltaic and shelf environments. So what we have here is we have a sequence of rocks which are being deposited along a coast. Sometimes when the sea level is lower, those rocks are going to be continental in origin because they're above sea level, and as the sea level begins to rise again, you're going to see the rocks will transition from continental rocks into intermediate type rocks. So you're going to get beach deposits or maybe lagoonal deposits, and then over the top of those, as the water level keeps rising, you're going to get marine deposits being deposited. So the initial units of your cyclothem are represented by deltaic and fluvial deposits. So these are river-related deposits. So fluvial, river, deltaic, obviously a delta, which is also going to be a river-related process. So we know we've got to be near the coast because we have deltas, and we know that we have large quantities of clastic sediment being moved into the area through rivers, and we can see that from these sediments. Now, these continental / coastal sediments are then overlain by what's called the underclay. And the underclay is a layer of rock that's obviously, as the name suggests, very clay rich, and it contains numerous root casts. That should say casts, not clasts, my apologies. And so this is telling us that what we have is a layer of clay that's got lots and lots of trees growing in it. Now, the underclay itself represents a lagoon deposit. So what it is we have a lagoon, an isolated body of water located along a coastline. This lagoon is full of trees, and it's these trees which are going to essentially provide the organic material which is going to lead to the formation of coal beds. So here's our situation in the late Carboniferous. So the areas marked out in black circles here are areas where we have large-scale coal formation taking place. And so these are areas which will be sporadically transgressed over and then regressed over as the sea level rises and falls. Now, one of the things that's going on in the Carboniferous is we have numerous periods of glacial expansion and retreat, and this is obviously going to cause the global sea level to rise and fall. Remember, as glaciers grow and get larger, they lock up water and the global sea levels will drop. When glaciers melt, the water returns to the ocean basins and global sea levels will rise. So in the Carboniferous, when we have these glaciers expanding and contracting, that's obviously going to cause the sea level to be rising and falling quite a lot, and that's going to lead to numerous smaller marine transgressions and regressions. And so these coastal areas are going to be constantly being transgressed over, regressed, transgressed, regressed, etc. And this is going to lead to the formation of the Cyclothems. The other thing to remember, of course, is that we are also in an environment that's located approximately along the equator, so we're going to have a relatively hot, relatively humid climate, which is perfect. So we've got swampy conditions in a hot, humid climate. Those are the perfect conditions for forming coal deposits. So the coal bed itself forms by a buildup of organic material, so that's plant material, in these swampy lagoons. So the plants die, they fall into the water, but they don't decompose. And that's because the water in the lagoons is once again anoxic. There's so much organic material going in that the decomposing organisms in the water, well, they begin to decompose the organic material, but they very quickly use up what oxygen there is in the water, and so eventually the water becomes anoxic, oxygen free. This means later on any organic material that falls in will not decompose, and so you end up building up a big thick layer of organic material in the bottom of your lagoon, and this layer of organic material will be liquefied and turned into coal. Now, these coal beds are then overlain by a sequence of marine carbonates and mudstones, usually with abundant marine invertebrate fossils. So this is due to the marine transgression continuing and our lagoon being covered over by the sea. And so when this happens, obviously we're going to get marine deposits over the top of our lagoon deposits. So the marine interval will end with an erosional surface, so that's telling us there's been a marine regression, so the sea has come back off the land. That will then expose the marine sediments. They will be eroded, and then we'll obviously see fluvial sediments being deposited over the top, because what we have once again is now exposed continental crust or continental rocks, and then the entire process will start again when the next small marine transgression begins. And so this leads to a sequence that looks like this. So here are our continental fluvial sediments. So that represents essentially a non-marine continental environment. We then begin to see the deposition of the underclay and the coal seam. So these are our lagoonal environments. That's telling us that the sea level is rising. And we've got a swampy environment, a bit like the Okefenokee, like here in Georgia. Then we begin to transition into a sequence of sands, muds and carbonates. So this is going to be the marine sediment. This is telling us we've got a full marine transgression and our swamp is now covered over by the ocean, or the sea should I say. And then we see the marine sediments disappearing. We go back into these coal forming swamps for a little while, and then we come all the way back to terrestrial rocks. So this is a period of erosion where we're going to see rocks being destroyed, we're going to see fluvial sediments being deposited, and then the next cyclothem will begin when the sea level begins to increase again. And so we see these again and again along the coastline of Laurentia during the Carboniferous. And so this is telling us a lot about the types of environments that are going on, and it's also telling us about these glacial expansions and retreats during this time period. So as I said, cyclotherms represent these transgressive regressive cycles. And obviously they're separated from one another by the erosional surfaces. And the erosional surfaces just simply say, right, the sea's retreated, the land's now exposed, there's a period of erosion, and then the next transgression will begin. So because of this, because we have this erosional surface at the top, it's not uncommon for you to lose the upper portion of a cyclothem. So if we just go back a second, so it's not uncommon for these marine sediments, for instance, to be missing and having been eroded away. As long as the coal persists, that's what people were mostly interested in, obviously for economic reasons. So in terms of the regressive sequence, when the sea is retreating, it typically goes from carbonates. They'll typically transition into more muddy sediments, and then eventually you'll go on to intermediate sediments like beach deposits or lagoonal deposits, and then you'll end up with continental sediments, assuming that part of the sequence hasn't been eroded away. So just to give you an idea of a modern example, so here's the Florida Everglades. So you can see it's a swampy area. Okay, you can also see it has very, very large amounts of organic material. I mean, you can quite clearly see the green colour here. If you've ever seen a picture of the Florida Everglades, you know it's absolutely stuffed with plants. It's a relatively topographically low area, so it's essentially at sea level, so it doesn't take much change in sea level for the area to be inundated and become swampy. We also have large quantities of, we also have quantities of clastic sediments being transported in by these short rivers here. So in this case, what we have is we have a lagoonal environment, we have muddy sediment going in, we have lots of organic material. All that organic material is going to cause the water to become anoxic, and so that's going to inhibit decomposition. And you can see the dark colour of the water here, the kind of, rather murky looking appearance. That's a combination of the clay-rich sediments being deposited by these short rivers, and the large quantity of organic material mixed in with these sediments helps to give it this rather uninviting black-brown looking appearance. So as we've touched on, the best explanation for these widespread sea level changes during the Carboniferous is the advance and retreat of ice sheets. So when we actually look at this late Paleozoic cyclothem activity, it seems to correlate very, very well with the information we have on the growth and retreat of glaciers, which is going on the Gondwanan supercontinent during that time period. So everything seems to match up quite nicely. Okay, so this is a good place to stop. So stop the presentation, get up, have a walk around, get a glass of water, sit down for 5 or 10 minutes, relax, and then please come back for part 3.